Welcome back to Simplifying Synthesis. In this video, we are going to look at the total synthesis of cyclopamine. This work was carried out by the Baran group and was uploaded to Chem Archive in August of 2023. Cyclopamine was first isolated from Veratrum californicum, more commonly known as the California corn lily. It is an inhibitor of the hedgehog signaling pathway, which is critical for the correct differentiation and development of embryos. Most famously, this can lead to the cyclopia birth defect in sheep, where they are born with only one eye. Despite this, the compound has promising anti-cancer activity and several analogues have been reported. The cyclopamine framework presents quite an interesting challenge for synthetic chemists, as it features a C-NOR D-homosteroid skeleton with the D-ring appended to a spirocyclic THF motif. This D-ring also contains a tetrasubstituted alkene, while the E and F rings are fused via a rare 6,5 trans junction. To construct the spirocyclic centre, they would use a lithiate addition, while the central alkene could be generated using alkene metathesis. To form the F ring with the correct stereochemistry, they would use an asymmetric allylic alkylation, followed by halocyclisation. So let's start with the synthesis. This began with the protection of the Wieland-Miescher ketone using ethylene glycol. The enone was then isomerized by first treating it with potassium terbutoxide to deprotonate the gamma position, forming an enolate. This enolate was then treated with acetic acid, which reprotonates it at the alpha position. Sodium borohydride was then added to the reaction mixture, and this reduces the ketone by attacking from the bottom face to produce the target compound in a 68% yield with a greater than 20:1 DR. In addition, a 15% yield of the allylic alcohol was obtained. This results from the reprotonation of the enolate at the gamma position. This alcohol was then protected using benzyl bromide, and the acetal was then deprotected in a 91% yield using PTSA. Taking this ketone forward, an enolate was formed using LDA, and this then attacked an alkyl bromide bearing a phosphonate functionality. This was taken forward as a mixture of diastereomers, and the enol ether was then hydrolyzed using hydrochloric acid. With the phosphonate in place, they could then carry out a Horner-Wadsworth-Emmons reaction. Cesium carbonate deprotonates the position alpha to the ketone and the phosphonate. This then undergoes an intramolecular addition into the cyclohexanone, producing a new 5-membered ring. The resulting alkoxide can then attack the phosphonate, forming a 4-membered oxophosphate intermediate, similar to that formed during a Wittig reaction. This intermediate then undergoes a cycloreversion, forming a new carbon-carbon double bond to complete the enone in a 42% yield with a 9:1 DR. This compound was then recrystallized to provide the desired isomer with a greater than 20:1 DR. With this compound in hand, the alpha position was then deprotonated with lithium HMDS, generating an enolate that then attacked tert-butyl bromoacetate. This formed the product in a 93% yield with a greater than 20:1 DR. The stereochemistry is likely guided by the concave shape of the molecule, which blocks the bottom face due to steric hindrance. In the next step, the carbon-carbon double bond of the enone system was reduced. 1,2-bis-diphenylphosphenobenzene was first reacted with copper acetate in the presence of polymethyl hydrosilane. This forms a copper hydride species that selectively undergoes conjugate addition to the enone system, as it is a soft nucleophile and preferentially attacks the soft electrophilic site. The resulting enolate intermediate is then protonated by terbutanol, generating the product in an 86% yield. This product was formed as a single isomer in the more stable trans configuration. This can be rationalized as resulting from steric hindrance from the methyl group on the adjacent carbon, blocking the top face of the ring. In the next step, the ketone took part in a Wittig reaction. Methyl triphenylphosphonium bromide was first deprotonated by potassium terbutoxide, generating an ylide that reacts with the ketone to form an oxophosphatane intermediate in a similar manner to the HWE reaction we saw earlier. Cycloreversion of this intermediate generates the exoalkene in an 80% yield. In the next step, the tert-butyl ester was reduced using dibal. This adds a hydride, and the resulting alkoxide intermediate eliminates an equivalent of butoxide. The aldehyde can then be reduced in a similar manner, and the primary alcohol was produced in a 91% yield. This alcohol was then iodinated using an Appel reaction. Triphenylphosphine reacts with iodine to generate phosphonium iodide. This is attacked at the phosphorus by the hydroxyl group, forming an activated intermediate that can then be displaced by the iodide. This eliminates triphenylphosphine oxide to generate the primary iodide in a 63% yield, completing the synthesis of Fragment 1. The synthesis of Fragment 2 started with an asymmetric allylic alkylation of a siloxyfuran. This is reacted with methyl allyl acetate together with the palladium catalyst, a chiral ligand, potassium carbonate, and ammonium acetate. The palladium complex first reacts with methyl allyl acetate, eliminating the acetate and generating a palladium coordinated tert-butyl cation. In conjunction with this, the silyl group is also lost, generating an alkoxide that allows for the C5 position to act as a nucleophile and attack this cation to stereoselectively install the allyl group. This selectivity results from the chiral catalyst used, which is proposed to form a hydrogen bond with the alkoxide. While these alkoxyfurans typically react through the C3 position, the steric hindrance provided by the ligand blocks this and allows for the preferential reactivity of the C5 position. This ligand also blocks one face of the molecule, and therefore the cation can only react with one face of the ring to generate the product in a very high EE. Taking this forward, it was reacted in an azomichael addition with N-benzylsulfonyl or benzyl hydroxylamine. This stereoselectively undergoes a conjugate addition, attacking from the face anti to the allyl group. With this complete, the benzyl group was reduced using zinc and ammonium chloride to produce the product in a 71% yield with a 71% EE. This could be crystallized, isolating the product with a greater than 97% EE. The next step involved the construction of the key trans 5,6 ring junction between the E and F rings. They did this using a halocyclisation, using the rationale that in this system, a 5-exotrig cyclisation that would form a trans 5,5 ring system would be disfavoured due to the strain transition state, and instead, the 6-endotrig cyclisation would be preferred. The mechanism that they propose for this reaction involves the formation of a nitrogen-iodine bond that then undergoes homolysis to produce an N-centred radical. This then attacks the alkene on the less substituted side, forming the 6-membered ring and generating a tertiary radical. This radical can then react with another equivalent of iodine, generating the tertiary iodide in a 51% yield with a 20:1 DR. This iodide was then removed using AIBN and tributyl tin hydride. The AIBN first undergoes homolytic cleavage to generate a radical that abstracts a hydrogen atom from the tributyl tin hydride to generate a tin radical. This can attack the iodide, leaving a radical residing on the tertiary carbon centre. This goes on to attack another equivalent of tributyl tin hydride to regenerate the reactive radical species. This forms a dehalogenated product in a 71% yield, with the methyl group occupying the more stable equatorial configuration. In addition to this product, they also formed a ring-opened byproduct, similar to that used to carry out the halocyclisation. With this in hand, the position alpha to the ester was then methylated using lithium HMTS to generate an enolate and methyl iodide as the electrophilic methylating reagent. This formed the product as a single isomer, with the methyl group in a configuration anti to the hydrogen of the tertiary centre. With this in place, the compound was then reacted with 2-lithiopropene, which adds to the ester and eliminates the alkoxide byproduct, breaking open the lactone ring. This alkoxide was then reacted with Tes chloride to generate the silylated product and complete the synthesis of Fragment 2. With this complete, they then moved into the endgame of the synthesis. Fragment 1 was first reacted with tert-butyl, generating the primary lithiate, and this then attacked the ketone of Fragment 2 that was activated by a solution of lanthanum trichloride, bis-lithium chloride. This coordinates to the carbonyl oxygen, increasing its electrophilicity and drives selectivity for 1,2 addition. This reaction formed the product in a 71% yield, and its structure could be confirmed by X-ray crystallography. In anticipation of a Suji-Trost reaction, the hydroxyl group was then Bock protected using Bock anhydride and potassium HMDS, and the TES group was removed using HF in pyridine. This formed the target compound at a 95% yield over 2 steps. With this complete, they could then carry out the Suji-Trost reaction. Palladium acetate and triphenylphosphine react with the Bock group, promoting its elimination and the formation of a tertiary carbocation. This undergoes intramolecular attack, forming a 5-membered ring in a 73% yield. It is worth noting that this Suji-Trost reaction was quite difficult and required screening over 20 reaction conditions in order to find the optimum method. It is for this reason that they used a Bock group instead of the more commonly used acetate. With the EF rings now complete, they turned their attention towards the formation of the central D ring. This was completed using olefin metathesis. This reaction involves the formation of a tetrasubstituted olefin, which is quite a difficult transformation to achieve. This difficulty necessitated the screening of many catalysts and reaction conditions in order to find the optimum method to achieve maximum yield. They discovered that they could use a 60% loading of an indenylidene catalyst in perfluorotoluene to achieve full conversion of the substrate. In an olefin metathesis reaction, one of the alkenes first undergoes a 2+2 cycloaddition with the ruthenium-bound ligand, generating a 4-membered cyclic intermediate. This undergoes a cycloreversion, eliminating the ligand and generating an intermediate with the substrate now bound to the ruthenium catalyst. This then undergoes an intramolecular cycloaddition, once again forming a 4-membered intermediate that can undergo a reversion to form the desired tetrasubstituted alkene in an 85% yield. With this ring formation now complete, a simple deprotection of the benzyl and sulfonyl groups using Freeman's reagent completed the synthesis of cyclopamine in a 78% yield. Well, I hope you enjoyed the synthesis. Join me in the next video where we will look at the total synthesis of nabsessin C.